Okay, so let's continue with our module 9. And as I was mentioning to you earlier, module 9 is something that all of you should be making flashcards for. We will also be doing a little bit of mechanisms in this module, but most of the mechanisms and the reactions that you are going to see is something that you will need to memorize the reagents. For binary reagents, for polar binary reagents, a common mechanism works here. The pi bond will be the electron rich site, and it is going to abstract out the electrophilic part. For example, in HX kind of a reagent, H will be the electrophilic, electron deficient part. So the electron rich attacks the electron poor, and the bond between the electrophile and the other partially negative site will get broken. A stable carbocation will form, okay, out of these two possibilities. The carbons which were involved in the formation of the pi bond, between those two, a stable carbocation will be formed. And hence that is what our regiochemistry will dictate, the Markovnikov's rule. Markovnikov rule states that the electrophilic part will go to the less substituted carbon, or the nucleophilic part will go to the more substituted carbon. And for these two statements to be true, it is just an indication that a more stable carbocation will be the intermediate for your final product. So make sure that you all draw your starting materials, draw your products out. Okay. I was grading my module 7 test, and some of the students did not draw the products correctly because they did not know how to make the connections. Okay. So all your binary polar reagents, make sure that you can identify the electrophilic site and the rest of the nucleophilic part. This is your nucleophilic site, the electron-rich site, which is going to attack the electrophilic part, kicking out your partially negative charge part, which will later, of course, attack the other carbocation. So between the polar binary reagent, electrophilic part goes to the less substituted carbon, and the nucleophilic part goes to the more substituted carbon. Markovnikov's regiochemistry, Markovnikov regiochemistry, Markovnikov. The only time we will see an anti-Markovnikov or anti-Markovnikovs is when you will have a peroxide and an HBr combination. This does not follow your electrophilic addition reaction. This is what your electrophilic addition mechanism and reactions were. This follows a radical mechanism, and we will cover this special mechanism when we go to module 10. In this case, this particular carbon is the more substituted carbon. So ideally, the Br should have gone here. However, because of the presence of a peroxide, and a peroxide will look something like this, the Br will go to the less substituted carbon. Now this combination is only true when HBr and a peroxide are present. This combination will still give you a Markovnikovs if peroxide has some other acid, not HBr, some other acid, HCl, H2O, H2S, or something like that. Only this combination is going to give you your anti-Markovnikovs rule. And in terms of reactivity, HI will react the fastest, HCl will moderate, HF will not react. It will be too violent, out of control, and we will not be able to do it. And we looked at 3 ways by which alcohols can be generated. One is when you have acidic dilute acid, that is adding on across the double bond. It follows the Markovnikov's stereochemistry, and we cannot control the stereochemistry. Why we are not able to control the stereochemistry? Because a carbocation will be generated. Whenever a carbocation will be generated, a rearranged product will be formed. Whether it is the formation of alcohols with alkenes and this acetic acid, or it is the formation of a SN1 reaction, or it is a formation with a E1 kind of reaction. SN1, E1, and this electrophilic addition, all of them have a carbocation intermediate, and you will get rearranged products. The second way by which we form alcohols is by oxymercuration reaction, where we have these reagents. The mercuric acetate in presence of a solvent and sodium borohydride. Now, on the slides, I had shown you water. If you have any other protic solvent also, that will also be attached here. That will be the one we'll be attaching here. What is the mechanism? We looked at the mechanism. It was a bridged intermediate. So it was a bridged intermediate, something like this. So the electrophile, the electrophilic part, gets added first across the double bond, and this is on one side. So where will my nucleophile attack? The nucleophile will attack the more substituted carbon. So if this is in this form, this OH will be appearing something like this, because the OH, or the incoming nucleophile, attacks from the opposite direction, not the same direction as the electrophile, but from the opposite side of your electrophile. So that is something that you have to remember. And we are going to look at some more examples today with this particular reaction. And we also did a 2-step synthesis here. If you have a alkyl halide, something like this, and you add sodium ethoxide, what does sodium ethoxide do? It is a strong base, secondary alkyl halide. You are going to have E2 product as your major product. What if instead of this sodium ethoxide, I had added potassium terburoxide? Now, this is still a strong base, but a strong, bulky base. Will I get the same alkene? I will not get the same alkene. My regiochemistry for this is a zigzags. More substituted alkene was formed. This is a tri-substituted alkene. The more substitutions you see across an alkene, the more stable that alkene is. But with a strong and bulky base, this is not the beta hydrogen that will be taken out. So this was the beta hydrogen that was taken out when sodium ethoxide, or a regular base, attacked. But when you will have a bulky base, a less substituted carbons, beta hydrogen will be abstracted out. And this is the kind of alkene that I would get. If I had used the same reagent here, the same reagent, mercury acetate. Let me just put water. And then sodium borohydride. What would be my product be? I would get a Markovnikov's product and in an anti manner. So I am going to draw my product exactly like this. I have to get my incoming nucleophile at the more substituted carbon. So between these two carbons, A and B also, this carbon is not substituted at all, whereas this carbon has at least one substitution. So this is where your incoming nucleophile will go, and your hydrogen, which will be after this sodium borohydride. So remember, this also follows a radical mechanism. We are not going to look at that. Just trust me on that, that a hydride replaces the mercury acetate. But this regiochemistry is still Markovnikov's. What does Markovnikov mean? The nucleophilic part of the binary reagent goes to the more substituted carbon. And what is my stereochemistry? It is still anti. Because the mercury was making an intermediate on one side, the attack of the nucleophile occurs from the opposite side. So this is all that this anti indicates to us. The stereochemistry is anti. Any questions so far? So look at the differences of these two structures. So this is a two-step synthesis. This is also a two-step synthesis. And the third way by which we can add alcohols to alkenes is by the hydroboration reaction. In this, you will get a borane in presence of your solvent, which is water here, peroxide and OH. This also follows a radical mechanism. So this mechanism and the HBr and H2O2 mechanism, we are going to look at it when we go to module 10. Okay. And the last kind of reactions, so the regiochemistry is anti-Markovnikov's. The OH will go not to the more substituted carbon, but to the less substituted carbon. So this is what you need to know about this. When you're doing the addition of alkenes with halogens, you will either use a polar nucleophile or a non-polar solvent or a non-nucleophilic solvent. With the non-nucleophilic solvent, you will also still get that cyclic bridged intermediate, just like you had in mercury. So mercuration and halogenations across the alkenes will give you a cyclic bridged intermediate. In both the cases, you will get a regiochemistry of Markovnikov's, stereochemistry of anti. Regiochemistry of Markovnikov's, stereochemistry of anti for both your mercuration reactions and for your halogenation reactions. So this was one of the examples that we had looked at on Friday. The only issue with these are when you will have a nucleophilic or a protic kind of a solvent. In this part, your regiochemistry is still Markovnikov's. The incoming nucleophile will attack the more substituted carbon, and the less substituted carbon will get the bromine. These two will be anti to each other. So they will be anti to each other. So for your module 7 onwards, whenever you're trying to decide about a product, always think of your mechanism. Okay, so I have tried to concise here what we are going to see. I want all of you to copy this. Did you get a chance to copy this, or maybe I wrote it later? Go ahead and copy these examples. So this is going to be A, B, and C. Everybody has copied these? Anybody needs to copy this? So in a few minutes, you might not see this page anymore. I'll give you a minute more to copy. So this is chlorine and water. So Cl2. So this is Cl2 and H2O. This is what it is. Does that answer your question? Okay, good. Now, so far, we have been looking at everything that our alkenes are doing. So let's just focus on alkenes for a couple of more minutes, and then I will show you how alkynes have similar reactivity, just like our alkenes. Now, if we were in a regular semester, this is where your module 9B would start. But just remember, because we are doing a fast pace summer session, we are not going to have any drill test 9B. All of your modules from 9A and 9B are going to be combined together for your drill test on Wednesday. Okay? So oxidative cleavage of alkenes. And this is what I want all of you to know. Oxidative. What does oxidation mean? Oxidation means when you are adding oxygen. But in the process, you are also reducing the number of carbons. So this reaction, this particular reaction that we are going to see today, it depicts, it is just the opposite of adding on the number of carbons. If you have number of carbons and you want to increase them, you use a different methodology. So that is a synthetic strategy. This is also a synthetic strategy where we will have ozone, zinc in presence of acid. So either HOAS or methyl dimethyl sulfide, either of them. Now, what is the mechanism that we see here? You don't need to know the mechanism for this reaction. Just understand what will happen. The oxygens from the ozone will be attaching themselves across the carbon-carbon double bond. Okay, and they form an intermediate, and several steps later, you will get the product. But what is it that you should do? Let's say that you are given this particular product, CH3, C, CH3, and I will just elongate this particular double bond right here. And in the double bond, within the double bond, I'm going to insert 2 oxygens. What does this do? I got one product here and my other product right here. So let's see. Oxygen with CH with the CH2, CH3. And then CH3 right here with this C, this CH3 and the oxygen. So instead of having a carbon-carbon double bond, I now end up with a carbon double bonded oxygen or a carbonyl functionality. However, with decreased number of carbons. Do you see what happened? What just happened here? Let's look at a few of our examples. This is one of the simplest and easiest of the reactions that we see here. Write this down in your notebook or on your paper, wherever you're writing something. And I will give you an easy way to look at it. Because on your exam, you will get a more complicated version, maybe something like this. You know, so you will have to recognize where the double bond is. And I have my ozone with zinc, and I can use H positive. This can be from acetic acid also, or I could use zinc with dimethyl sulfide also. What is my product going to be when I'm doing ozonolysis? Ozonolysis is going to cleave my product. I'm going to insert an oxygen here and an oxygen here. I'm going to break these two groups or products. I'm going to write exactly this. CH3, C double bond O, H. So instead of writing a C double bonded C, I'm writing a C double bond O. Also, CH3, what has happened here? Double bond O. So these two are my products from this particular ozonolysis. Any questions? Okay, very good. Because ozonolysis does constitute a little bit of more tricky mechanism or tricky part, as I would say. Okay, so the CH2 part and the CH3 part. You can use other reagents also in this, but having a dimethyl sulfide is a very common thing also. The other reactions of alkenes that we will look at are dihydroxylation. So this is one of the reactions that we have seen, the oxidative cleavage. The next will be the diol formation or dihydroxylation. This can be done in two manners. The first is when you use a metal ion. So as you're seeing here, we have metal ions, KMnO4, cold, in presence of base and water. Now it does look like a big bulky reagent or number of reagents, but as you will use them, you will get used to them. And make sure that when you write KMnO4, you definitely want to insist on cold conditions. So sometimes you might also see KMnO4 hydroxide water minus 30 degrees Celsius. Okay, so did I tell you that it is cold? Anybody? Did I tell you it is cold or not?
Yes.
Yes.
Yes, very good. So you have to make sure that you take care of the conditions. Having cold KMnO4 is very important. Otherwise, your dihydroxylation will not occur. Something else will occur. We are not going to cover that part in our course today. Or you can also use osmium tetroxide with sodium sulfite or sodium bisulfite in water. Having water is very important part because you want to give your OH across the alkene. So let's look at two examples actually. Oops. Let's look at this example right here. We're going to use the same structure. So using metal oxides, when you will use this metal oxide, you can use KMnO4, base, water, cold, or you could use osmium tetroxide, NMO, or sodium sulfite, water. So what is it that I'm going to see? With both of these reactions, one of the common intermediate will be this intermediate. So in KMnO4, it is Mn. In osmium tetroxide, it is osmium. That is the only difference. Okay, but the mechanism is going to be same. So KMnO4 or osmium, we'll just treat both of them as this M. Both of these metals have 4 oxygens on them. So they can they can be added across at least 2 alkenes. So this metal ion, both the oxygens add from the same side. When they add from the same side, we say that this is a syn addition. So what is the stereochemistry? It is syn. What is the regiochemistry? We don't know. There is no regiochemistry involved here. Okay, there is not more substituted or less substituted. Both carbons get the OH at the same time. So just knowing this intermediate is very important for you. You don't need to know what are all the other multiple steps that happen between it. Any questions? So let's look at these examples right here. Okay, don't worry about this hot. We are not looking at hot KMnO4 anymore. We will just be focusing on our cold KMnO4. So if you look here, the M metal is here, oxygens will be here. So both of these alkene carbons will add OH from the same side. So what is this enantiomer that we will get? OH. Right? So don't worry about the hotness. The only time that you should look at cleavage is when we have ozonal lysis. That is the only form of reaction that you should look at. So what is the product that I'm going to get here? I'm going to draw my methyl groups. These are my hydrogens. Don't forget the hydrogens. And what is it that I'm going to get? I'm going to get a diol. What about with osmium tetroxide? I'm going to draw my product, the basic structure. Are there any hydrogens across these carbons? No. So the only 2 things that are left are this OH. So what is my stereochemistry for both? Syn attack occurred across the alkene. Both the groups attached on the carbons from the same side. What is the regiochemistry? Not. We cannot control the regiochemistry. It can attack from the top, it can attack from the bottom. Same racemic mixtures will form. Okay. Another kind that we can do for the diol formation is when you form from epoxides. Now we will learn how to make epoxides. But what is an epoxide? An epoxide is a CH or CC oxygen inserted between an alkene. So across the alkene, when you have an oxygen sitting between them, now this is quite stable but still reactive, more reactive than the alkene. How is this formed? We are going to look at it in a minute, but the diol, we are working on diols, right? Let me introduce the acidic conditions when I'm adding water. Now, just like your cyclic bridged intermediates, could the incoming nucleophile attack from the same side? It cannot attack from the same side. It will attack from the anti-side, not from the same side, but from the opposite direction of your OH. So our stereochemistry will be anti. If you're using an acidic acid or acidic conditions on your epoxide, you will get your incoming nucleophile to the more substituted carbon. So the Markovnikov's rule will be applied when you have acidic conditions. So the incoming nucleophile will attack. Both of these are same, so I'm not going to worry about that. When the incoming will attack, this bond will break. Just like you broke for mercury, just like you break for your halogen, bromine and chlorine. So my OH right here and another OH right here. And this my H, this my H. Remember there are two hydrogens also on this. So from an epoxide, when you will make a diol, you are going to get an anti-diol. But using these metals, when you are going to make a diol, you are going to make a syn diol. They will be on the same side. I'm just making one type, the other type will be there. The one type, the other type will be there. Do you all understand what the En term En means? The enantiomer. Any questions on this so far? So how are these epoxides formed in the first place? So knowing these reagents will definitely help you with your synthetic strategies. So when you form the diol, this is how we're going to make a diol. Let's look at epoxides now. So this is just the mechanism of formation of a diol from an epoxide. And you see this is the plane. Your epoxide is on one direction. The incoming nucleophile comes from the other direction. So an anti kind of a product is forming. So this is a SN2 mechanism. The leaving group is on the other direction. But how are these epoxides formed? So first of all, make sure that you can identify an epoxide. It is just a triangular thing. In a cyclopropane, you have 3 carbons. In an epoxide, you have only 2 carbons and 1 oxygen. And what you need is this particular peroxy kind of a bond. Now this peroxide kind of a bond is very important for the insertion of oxygen. So one of these extra oxygens will be inserted in a syn fashion, of course, a syn fashion. The oxygen needs to be on the same direction, the same plane from across the alkene. But this addition, when you do the addition of an alcohol or a dilute acid, that is completely anti. Stereochemistry is anti. You cannot control the regiochemistry in here. But if you have acidic conditions, the nucleophile, the regiochemistry is Markovnikov's. When you have a basic condition, then your regiochemistry will be anti-Markovnikov's. Still, stereochemistry anti, because of the presence of this epoxide, your incoming nucleophile will attack from the opposite location. So still the stereochemistry is anti, and in acid catalyzed also the stereochemistry is anti, because the incoming nucleophile still attacks opposite from that of your actually I should show it like this. So still anti-products will form. So knowing your epoxides, the stereochemistry is anti for all of the conditions, but you need to remember for your own synthetic strategies what will happen when your conditions are acidic. With acidic conditions, a carbocation will be generated. Whenever a carbocation will be generated, it will generate to form a more stable situation. And where is the more stable situation? When the incoming nucleophile goes to a more substituted carbon. That is what the most stable condition would be. But when you have a base attacking, the base do not have a carbocation intermediate kind of a thing. And so for steric reasons, it goes to the less substituted carbon. So knowing these two things is an important factor for you to be able to make diols and any functionalizations across a double bond. So if you will see down the lane also, whenever you will have a functional group on two adjacent carbons, either in the form of this or in the form of this, you should always think that your starting material came from an alkene. Your starting material came from an alkene. That is why you will have adjacent functionalizations of your groups. So that should be part of your synthetic strategy. In your book, you will see several other examples also, but I just want to show you a few here. So let's say that you're given a sequence like this. How are you going to solve for it? Of course, you're given the starting material and you're given this peroxy kind of a condition. You will remember that you will need to form an epoxide. Whenever you will have a carboxylic acid also, so this is an acid. You have just inserted an extra oxygen in this. So this has now become a peroxy acid. What about this R group? This R group is simple alkyl. It could be any alkyl. It could be a methyl group. It could be a phenyl ring, or more commonly, it is a meta-chloro group. So a meta-chloro peroxy acid, commonly known as MCPPA, peroxybenzoic acid. You don't need to know the name of this, but you should definitely know the abbreviation for it. R, anything R with this bulk should give you an indication that an epoxide will be formed. And so where am I going to put my epoxide? Across this double bond. So I'm going to draw my product. I will not draw my alkene. I will draw my oxygen right here. And now I have sodium methoxide. Tell me, is it acidic or is it basic? Because of the presence of a sodium ion, this material comes from sodium hydroxide. Sodium hydroxide is a very, very strong base. So this is basic conditions. Where is my incoming nucleophile going to attack? At the more substituted carbon or at the less substituted carbon? Anyone? Under basic conditions, where will my incoming nucleophile attack? First of all, do you know what the incoming nucleophile will be here, from here?
The lone pair from the oxygen.
Very good, the negative part from the oxygen. Yes, very good, Nelson. And that is going to be my nucleophilic part. So in the acidic conditions, my incoming nucleophile goes to the more substituted carbon. Where will my nucleophile from the basic conditions go to? To the more substituted carbon or to the less substituted carbon?
Less substituted because it's anti-Marcon cups.
Yes, very good. And because of the steric reasons, thank you, Nelson. Because of the steric reasons, this incoming nucleophile will go to the less substituted carbon and kick out this OH. So I'm not be able to draw here. Let me try to draw it here. So if my OH was something like this OH will be here, and this oxygen, methoxide oxygen, will be at the back. Anti-additions, anti and adjacent to each other. Yeah. So knowing all your reagents with your alkanes is very important. Before we start doing more reactions, let's look at our alkyne additions also. Now, starting from your electrophilic additions, CH3, C triple bond, CH3. If I have any binary reagent, what happened with my alkene? When I had my binary reagent with my alkene, I did get hydrogen on the less substituted, and my more substituted was where I got my bromine or wherever my halogen was. So alkynes also follow the Markovnikov addition. So the regiochemistry will be Markovnikov's. In this case, Both of them have same substitutions. So by chance or per chance, let's just add it across one of our carbons. But now, what will happen now? Now my double bond cannot be saturated without following the further Markovnikovs. Among these two carbons, A and B, B is more substituted, and I'm following my Markovnikov's rule. So where will be the second mole or the second equivalent of my HBr come to? The H will go to the less substituted and the Br will go to the more substituted. So what kind of a, reagent did I form? I formed what is known as a geminal dihalide. Geminal means on the same carbon. So whenever you're going to add HBr or HX or H2AO, H2S, anything of that sort, you will need two equivalents. Why? Because there are two pi bonds, pi 1, pi 2. You will need to saturate both of them. You will need HBr. Now water does not get added directly. We will see a special reagent here. But let's do another one. Now let me add, instead of HBr, I will add Br2. And let's use our CBr4. Is CBr4 a nucleophilic reagent solvent or a non-nucleophilic solvent? It is a non-nucleophilic solvent. So I will definitely need two equivalents of Br. First, the first bromine will add, remember, anti-addition, but Markovnikovs. So regiochemistry is Markovnikovs, stereochemistry is anti. With my second equivalent, I'll get Br from the first one, and then from the second one, I will get Br anti to each other. Of course, in the product, it will not look different, but you should know where are these bromines coming from and how. So what you have now is a vicinal tetrahalide. So dihalide, tetrahalide. Vicinal on the adjacent carbons. So this is what your binary polar reagents would look like. This is what your halogenation across the alkynes will look like. So very similar. So this will be your first product and this will be your final product. This is what you should show when I ask you what is the product of this reaction. This is an intermediate kind of a reaction, intermediate that you should know will form. Very quickly, let's look at the next reaction that we should look for alkyne addition is our hydrogenation of alkynes. Now, it is stating here that when you will have standard conditions, and we did these standard conditions with what? Alkene, right? Whenever you will use hydrogen in case of platinum or nickel or palladium, you are going to reduce your alkene to an alkane. So a similar thing happens here also. Let's see, you have CH3, C, triple bond C, CH2, CH3, just for the sake of changing the structure. But this is the functional group that you should focus on. If I use hydrogen in case of nickel, I'm going to completely hydrogenize. So first, this intermediate will form. What kind of addition do I see with catalyst? Syn addition. And finally, what I would actually see in my hand after the reaction is done is this complete alkane. So from an alkyne, I'm going to get an alkane when I will use the standard condition. And this is done under pressure. Sometimes temperature is also used. However, when you want to reduce only one pi bond, and this is where you will be getting a lot of questions. When you want to reduce from an alkyne to an alkene only, you don't want to go, you want to stop and hold from an alkyne to a double bond. You don't want to go to a complete alkane. What do? You poison your catalyst. So for example, when we do the Lindlars, we add quinoline. Quinoline will kill or reduce the efficiency of palladium. Okay, so barium sulfate and palladium in presence of methanol and a little bit of quinoline. So when you are given a reaction, you might be just given these 4 words. You should be able to identify that this is your Lindlar's catalyst. This is first and very important. It will give you a syn addition and you will get a cis alkene from it. On the other hand, there is a second reagent also that can give you a cis alkene, nickel 2 borane, or also known as P2 catalyst. So P2 catalyst and the Lindlar's catalyst, they will do syn additions of alkynes and give you a cis alkene. Let's look at an example here. Let's use the same. Oh, are you all able to see my screen? Yeah. So let's do the same example right here. CH3, C, triple bond C, CH2, CH3. And I'm going to use my Lindlar's catalyst. What is my Lindlar's catalyst? Palladium with barium sulfate, methanol as the solvent, and quinoline. I can give you this, or I can just write Lindlar's catalyst. So how are you going to draw your product? You will first draw these 2 guys with a double bond. Why? Because we are killing the formation of complete alkane. We are going up only to a double bond. When you will use palladium, you are going to get a syn addition. Syn addition of hydrogen. Any questions? So syn addition of your hydrogens. This carbon also had a methyl. This carbon also had an ethyl. And so what is the kind of alkene that I'm going to get? A cysteine. Similarly, let's look at a structure like this. If I have a reagent like this, and I write nickel dinickel borane or P2 catalyst. So I can give you either of those. What is the kind of product that I'm going to get? How many carbons are here? 1, 2, 3, 4, 5, 6. So between 4 and 5, I'm going to have my double bond. This is also going to be a syn addition, right? So both my hydrogens have to be on the same side. Across these carbons, this carbon has a methyl group. And what does this carbon have? 1, 2, 3, a propyl on it. So I'm still getting my cis. The way I'm seeing it, the way I'm drawing it, if I had not done my practice, I would not be able to do it. Okay. Any questions? Okay. So this is what your cis alkene forming reagents are. What if you need to get an anti addition? Now, lithium or sodium, we will only use these reagents in ammonia or a amine kind of a reaction. Do you all remember your functional groups? What kind of an amine is this? Primary, secondary, or tertiary? Anyone? Nobody? Because
we can't see the screen.
Once you can't see my shared screen.
No.
This screen?
No. Yes. Okay, now it's okay.
Oh, it was not here earlier?
I expecting the other one. No, I'm sorry for that.
Okay, okay. So what kind of a amine is this?
Primary.
Very good. Yes. So I have a lithium ion and I have a sodium metal. So lithium or sodium metal, I can use either of these, either in ammonia or a primary amine. Why did I not use water here? Is water going to do something bad here? Or water can be dangerous here? So how many of you did the general chemistry lab 1 at Xavier? Or is there anyone who did not do their general chemistry 1 lab at Xavier? What will happen if you do lithium and water together? Do you remember your instructor had shown you in a beaker all those beautiful demonstrations? It is going to catch fire if you use water, and lithium hydroxide will be produced. Same with sodium. It is a very vigorous reaction with sodium and water. So whenever we are going to do this anti-addition of the hydrogens to alkynes to make a trans alkene, we will use these metal ions in ammonia or amine. And these solvents also help us in doing the mechanism. It's a single electron transfer mechanism. We don't need to know about that mechanism for our course, but it is very interesting for all of us to remember that our general chemistry is going to stay with us for the rest of the chemistry life. Okay, so let's look at the same molecule here. CH3, C with a triple bond, CH2, CH3. And now I'm going to put up lithium with ammonia. So what do I have? I have a metal ion, just the metal ion, and ammonia. No water, no any other solvent. So what is the kind of a addition I'm going to have? I'm now going to have an anti-addition of hydrogens. So across these two carbons, I'm going to make my double bond. I'm going to add anti-hydrogens. So I can add it like this. I can also add them or show them like this. It's completely fine. What is the alkyl group on this carbon? A methyl group. What is the alkyl group on that carbon? The ethyl group. And so what did I make? I made my trans-alkene. So know your reagents. Any questions? So it could be lithium ammonia. I could have also used sodium with ammonia. I could have also used sodium or lithium with ethylamine. What is ethyl? CH3, CH2. Okay. Now, in our 8th module, we had looked at the formation of alkenes and also alkynes. So probably we did not do many chemical reactions for the formation of alkynes, but this is how an alkyne is formed. For the formation of an alkyne, you will always use sodium hydride. And if you have a terminal alkyne, you will use the same reagent to make an acetylide ion. So for the formation of a alkyne and for the reaction of a terminal alkyne, you will be using sodium amide. Sodium amide is a stronger base than hydroxide. Very important point that all of you need to know here. When you have an acetylide ion, it can only react with the primary and methyl. So with less bulky substrates only. Not with a secondary halide, definitely not with a tertiary halide, ever. Why? Because it is a SN2 reaction. This is a very strong nucleophile, C negative. Very strong nucleophile. It needs to react faster with primary alkyl halide or a methyl halide. Not just methyl halides. When I say this, you can also have ROMS, ROTF, and so on and so forth, as long as you have a good leaving group with a primary site or a methyl site. Everybody understands this part? Very important reagent. Any questions from this? Oh, I'm sorry. So this is the product that I want to make. Go ahead and draw it out. CH3, the triple bond, and this carbon is connected to a CH with two CH3s. If I have to figure out what should be my potential starting materials should be, how would I do that? Any guesses? What are the two reagents? What are the two starting reagents that I must have for this product to form? Is there anyone who has not copied this structure? Anyone who has not copied the structure? Okay, everybody has copied? Okay, great. I'm going to send all of you to breakout rooms and I'm going to give you 5 minutes to think about this. And meanwhile, I'll pause the recording here. Okay, so make sure that you submit your work in the lecture course. You see where these assignments activities are? So you will go to activities under your lecture course, go to assignments, and that is where you will be submitting your scanned copy of this work. So I'll give you 2 more minutes to submit your work under this folder. Now we are looking at the alkyne additions, right? If you look at this particular reaction, the HCl and the halogenations, we already covered these two at the back. And we are now looking at the hydrogenation reactions. And we are also trying to figure out how do these alkynes can be formed. So we have looked already at the way you have a dihalogen using sodium amide. You are going to make a triple bond with more substituted carbon, not with the less substituted carbon, but with more substituted carbon. Had you used a stronger base, a bulkier base, then you could have formed a terminal alkyne. But in this particular case, where your base is regular sized base, you will get a more substituted alkyne. But the number of carbons that you see here are exactly the same. 1, 2, 3, 4. 1, 2, 3, 4. And so for this particular reaction, I had asked you to give me 2 starting materials, which will add together to give you a new alkyne. So probably these two have less number of carbons than the carbons right here. Okay, so make sure that you give this to me within the next few seconds. Coming back to our alkynes. So far we had only alkenes adding water or OH across it. Let me just tell you, it is not easy to add water on alkynes. When you will try to do that, first of all, you have to use a special reagent, HgSO4. This will add OH on the more substituted carbon. So Markovnikov's rule or Markovnikov regiochemistry rules. But when this happens and a pi bond breaks, an unstable enol will form. And if you remember your module 3, there is going to be a resonance that can occur here. But this is not called a resonance. It is known as isomerism. Isomerism just means an isomer forms. In a resonance, we only move electrons. But in this isomerism, a hydrogen moves from OH to one of these carbons. So because an atom is also moving, we do not call this movement of electrons as resonance. We call it as a isomerism. And so this is known as a keto-enol tautomerism. So this keto-enol tautomerism is responsible for formation of ketones from alkynes. Another very important synthetic strategy. Let's look at it on paper. So let's say I have a same structure here. Okay. From this structure, I'm adding HgSO4. Remember, when you were adding water on alkene, you would usually use the mercuric acetate, HgOAc. So we are using a similar reagent, HgSO4 in presence of H2SO4. Many a times you will see water also written. But what if water is not written? Please assume that H2SO4 will have some water in it. Okay, it is not completely water, or it's not complete H2SO4. H2SO4 36 molar is the highest concentration of H2SO4 that we know, and it has some water in it. So what happens is Markovnikov addition. The incoming nucleophile will go to the more substituted carbon. In this case, it can go to either one of them. Okay, if it was just a hydrogen here, not a CH3, then out of these two, it will only go to this carbon. So this is my less substituted carbon where the hydrogen will go. And this is my more substituted carbon where the OH will go. And the rest of the molecule stays the same. So this first part, this intermediate, is very important for all of us. Why? Because this is an ene-ol. Ene from the alkene, ol from the alcohol. So the ene-ol. This enol is going to go through a tautomerism, and this hydrogen will be transferred here. This pi bond will be transferred here. And a double bond oxygen will occur. CH, CH3, CH3. What functional group is this? It is a ketone functional group. In a similar manner, if you want to do an anti-Markovnikovs to this reagent, what is the reagent that we must add? Same as we used for our anti-Markovnikovs with alkenes. So instead of doing a Markovnikovs, I will now get an anti-addition or an anti-Markovnikovs addition. So that is the regiochemistry. I was getting a ketone here. Where is my incoming OH going to go? To the less substituted or the more substituted? Anti-Markovnikovs, OH will go to the less substituted. The double bond will stay. Carbon will, the more substituted carbon will get the hydrogen. Another ene-ol has formed, but a more stable, this hydrogen is going to go to your other carbon. This hydrogen stays. This carbon double bond oxygen forms. This carbon will get the two hydrogens on it and the CH with CH3s. What is this functionality compared to this particular one? Does anyone remember? This is a ketone. What is this? What functionality is this? So this is a aldehyde. So from the same starting alkyne using appropriate reagents, either the ones causing Markovnikov's addition or the ones causing anti-Markovnikov's addition, you can generate a ketone or an aldehyde. Any questions? So I know this is a lot of material to cover, but making flashcards or writing them again and again will definitely help you. And before I end the class today, I wanted to show you that slide again, just to all of you to think about how you derive information. So a few minutes ago, we had discussed you can only use a primary or a methyl group for leaving. So your RX can only be a methyl kind or a primary kind. Okay, so this BR can be any X, any good leaving group. That's what I mean here. So when I look back at the structure that we have to make, I have two choices here. I can either make my acetylide like this, right? 1, 2, 3, and this CH, CH3, CH3 with a good leaving group. Do you think this reaction will go? Is this a primary or a methyl substrate?
No.
It is not. Very good. And so, if I use this reagent, CH3 with my leaving group, plus this carbon right here, this carbon, CH, CH3, CH3, will this reaction go?
Yeah.
Yes, SN2. So do not forget your earlier modules also. And remember that for this particular material to form, you can only get, and make sure that you write a reasonable group, reasonable starting material. And you should, so if I give you a reaction like this, CH3OMS, CH triple bonded, CH, CH3, CH3, NaNH2. What does this mean for us? What will be the product that you will get here? So think about it. This is a terminal alkyne. This is a strong base. An acid-base reaction is bound to happen here. And this intermediate will form. This will then react. And the same structure will form here. Any questions? All right, very good. So we have completed this module, but I will insist upon that you do more practice. Tomorrow we have our exam during our class time, and we will be doing some more examples from Module 9. Even though this module is done, but I would like for all of us to practice more questions tomorrow. So what I would like for all of you to do is to pay attention, of course, to your exam too for tomorrow. But after that, please make sure that you start listing it out. I have also extended the time for your PLA 6 submission. Okay, so it'll be now, I think I increased 1 day for that, but make sure that you look at that also. It'll give you a more sense of what is it that you should be memorizing? What kind of reagents you should be memorizing? Okay. Right. I know it's a lot. I know it's a lot of new material, but you can do it. All of you can do it. Okay? Just make sure that you practice, you rewrite it, you make flashcards, and time permitting, we can discuss tomorrow how flashcards can be made. All right, I will see you guys in a few minutes for the drill test then. Okay.